Morning, everybody. We have for 10 o'clock slot, we have Tony Collins, CEO, founder of EonCoat. He's going to talk about corrosion on the soil-facing side of tank bottoms. Give it to you.
Thank you so much. I appreciate the courtesy. And thanks to all of you for coming. Hopefully I'll tell you something interesting today. If you don't mind, I'm going to walk down here amongst you. I'm more comfortable with the folks. And if you have questions, don't hesitate to interrupt me. I'm happy to answer. Today, what we're going to talk about is corrosion of the soil-facing side of tank bottoms. We're going to talk about how to fix it, talk about why it happens, we'll talk about some chemistry, how you solve this problem. Can I guess that the folks in this audience probably have tanks and have bottoms that have a rust problem? Is that accurate? All right. We're going to talk to you about how to solve that. You know, years ago, we didn't care that tank bottoms leaked. They've always leaked. And you could let them leach into the soil, and it was okay until along about the 60s or 70s. We got a little more environmentally conscious, and the price of oil went up. So all of a sudden, leaking tank bottoms becomes quite a problem, both from an environmental and a cost standpoint. A reasonable question might be, why can't you just use a coating to protect the surface just like you do every other piece of steel you want to protect from corrosion? Legitimate question. And the reason it's a problem is the way tank bottoms are made. Basically, the way you make a tank bottom is you drag plates into the structure, you overlap them, and you seal weld them, right? So when you seal weld this lap joint right here, you're going to burn the coating off the bottom side. So any polymer coatings you're going to burn right off. So that's why coatings don't work so good. You can see here one photograph of us welding on, and we'll show you some more videos of this, but you can see us welding on a coating, and what you don't see is you don't see that ceramic burning off of there. And the reason is it's inorganic, and so inorganic things can withstand a lot more heat than organic things, polymers. Another popular way to stop corrosion is cathodic protection. Now, cathodic protection is a wonderful idea. If you maintain all steels have a voltage at which they do not corrode. What causes corrosion is loss of electrons. If you create a low enough voltage on the steel will be gaining electrons, and so it doesn't corrode. That's what cathodic protection is. That's how it works. You basically force electrons towards the metal. As long as you do that, you're protected. It turns out that you have to maintain the voltage in a fairly narrow band for CP to work. If you have, you need to be, for steel, lower than minus 800 millivolts, give or take. But if you get too much higher than that, the reaction of that current or that voltage in water, particularly any saline water, will create sodium hydroxide, which is pretty rough stuff. So maintaining the voltage in a narrow band, not challenging to do if you're on a pipeline where it's insulated and you can maintain the voltage. But on a large flat piece of steel against the ground, maintaining that constant voltage all the way across that plate, pretty daggum difficult to do. I mean, on my car, maintaining 5 volts from the computer back to the fuel tank on an insulated wire is difficult to maintain it within 1/10 of a volt, right? It's not easy even on insulated wire at 16 feet. You think a couple hundred feet across a tank that's laying flat on ground, not insulated, just very difficult to make cathodic protection work. All right, so how do we solve it? How do we solve the problem? What we try and do is react the metal with an acid to alloy the substrate. What we try to do is create a protective layer on the coating by giving the steel something to react with other than oxygen. I'll get more into that in just a second. This reaction between the acid and the base forms a protective layer. And this protective layer is essentially an alloy. It prevents voltage from crossing the substrate and prevents corrosion because it's an inert layer. On top of that, we have a ceramic that forms, and that ceramic provides a constant source of phosphate that protects the, my apologies. The ceramic protects the phosphate or protects the steel by continually leaching phosphate. You always want to keep phosphate next to the metal to protect it. This is not new science. Other people know this. Our technology works better because of the concentration we're able to provide. More phosphate you got at surface, better corrosion protection. I'm going to show you a short video, and I'll describe it as it goes. What you see here is us welding a plate, and after we weld this plate, look at the side of the plate. Instead of a burnt off polymer, which is what you normally see, this is a short demonstration of how to apply the coating. Basically, we blast the steel, make sure it's not real wet. We spray the coating on there. Here we're using a cartridge gun to spray it. You can use an airless gun to spray it. It's two-component, but it sprays. You don't need any mask, or you don't need any special equipment to spray it. You could be in a shirt and a dust mask, and that's plenty good enough because there's no toxins and no VOCs. You don't smell anything. So what you see here is we've coated this plate. We've just coated this plate. Welder's attaching his lead, and he's going to weld it. So you watch this weld, and we're applying. The surface of that metal is going to get molten. The underside of it's going to reach about 1700 Fahrenheit. So 1700 Fahrenheit would burn off a polymer, but look what happens to the EonCoat. Nothing. No disbondment, no nothing. Most people see that and think that's not possible. This is why it works. I told you we formed an alloy layer. When you spray that ceramic on there, this gray area you see right here, it's an alloy. It's an alloy of magnesium iron phosphate. Phosphating steel is not a new thing. These are the chemical equations for how the process happens, how the alloy forms, and what have you. If you guys are interested in more technical discussion, I'll be happy to join you in it. I won't bore you with it right now. The alloy layer, looking at it in a scanning electron microscopy, looks like this. So what's happened here, if you were looking at normal phosphating, this would be crystalline. No matter how tight you pack crystals together, there's always gaps in them. But here, it's an amorphous layer, So amorphous continuous layer, nothing gets through. If you don't remember anything else I told you today, if you don't remember anything else, remember this. Corrosion is an incredibly simple thing, incredibly simple. It happens because iron loses an electron. That's it. It's no more complicated than that. Iron loses an electron. Iron loses an electron, and nature can't stand that charge imbalance. What makes something a conductor is it freely allows its electrons to give up and receive, right? Electrons continually pass in a conductor. So iron, like all conductors, easily can lose an electron, and when it does, then you got a problem. So remember this part. If iron loses an electron, what it's going to be like, it's going to be like a Boilermaker on a Saturday night in a bar. It's got to bond with something now. The charge imbalance is not tolerable. And it chooses what to bond with exactly the same way that Boilermaker does. I can say this, I worked my way through school in the crew as a Boilermaker. I can make this analysis, but it chooses what to bond with in exactly the same way. Anybody tell me what that way is? Whatever takes the least amount of energy. Whatever's the lowest energy state, that's what it's going to bond with. So, oxygen has an energy state, a Gibbs energy of like minus 700. Silicate's a little bit lower than that. Phosphate's much lower than that. But that's why inhibitors work. You give it something to bond with that enables it to form a stable alloy. If it forms with an oxide, it's going to flake off. But if it forms a stable oxide, a stable layer, it's there and it's permanent. This is a more detailed, this is a scanning electron microscopy picture of what this looks like. What you see here is we scraped off the ceramic and we're looking at just the alloy layer. And it's not thick, it's only a few microns. But compare it to the layer on stainless steel, which is angstroms, you're talking thousands of times as thick. I won't go through the third-party validation a lot. Amal Laborno was here last year and gave a presentation. I've copied some of the things that she presented. But I just thought I should tell you there's been some pretty smart people validate the testing. Charter did this testing and paid for by Chevron. But anyway, the key findings, she talks about OCP, linear polarization, and she did some testing before and after welding. The thing that was most interesting to me is that the adhesion actually improves over time. Not that adhesion is important to this coating. It doesn't really have to have adhesion because it's a porous thing. But the bond, what it tells you is that this is an active corrosion suppression system, not a barrier that's static. Static coatings are just barriers. They get worse all the time. This coating is anti-fragile. What that means is that the more stress you put on it, the better it gets. All right. I want to talk about one more thing. Before I let you go. It's wonderful that this coating is environmentally friendly. It's wonderful that this coating lasts a very long time. Those are all good things. But let me talk about why I spent the money to develop this. Let me talk about what really matters to me and why I think it should matter to you. By a show of hands, who in this group knows what a hazard assessment is? Okay, good. You guys have been in a plant. Who knows what a JSA is? Very good. Very good. You've been in a plant. Now, for you guys who've been there, who can tell me what are OSHA's 3 lines of defense? Come on, it's a requirement for your JSA. What's OSHA's 3 lines of defense? Somebody? Exactly. Who said engineering? Very, very good. There's an educated man back there. The 3 lines of defense that OSHA says, engineering controls. Eliminate the hazard. That's the first line of defense. Eliminate the hazard. Administrative controls change work practice. And as a last resort is PPE, right? PPE is, it isn't where you want to be, right? You're down to your last line of defense. So, this coating has no VOCs, no HAP, no odor, no toxin, and it outperforms the other corrosion coatings in the marketplace. So while we're doing our JSAs, why don't we ask that question? If we're going to eliminate the hazard, this is it, right? This is how the hazard goes away. We don't have to worry about painters being suited well enough or painters being... So for what it's worth, this mattered to me, mattered enough to me to sponsor this research. It eliminates the possibility. Painters tend to die young and die unpleasantly. This is a way to stop that. Sitting here with me is a genius behind this material science. His name is Samir Patel. And I asked him to sit in case you guys ask hard questions. I will answer the easy ones. Tell you what, I'm going to step back up here and pass this around. Somebody was going to hand this mic around for me, I guess. Go ahead, sir.
Does this coating shield CP? Have they tested it for shielding of CP?
Excellent. Oh, excellent question. Excellent question. The question was, does the coating shield CP, cathodic protection? You can use cathodic protection in conjunction with this technology. We've tested it multiple times. The thing that makes coatings fail due to cathodic protection is something I referred to earlier. If the voltage gets significant enough, you form a lot of sodium hydroxide. So if we test at 1 volt, 1.2 volts, or 1.5 volts, EonCoat does fine. It's passed all those tests. I run an R&D facility, so we're kind of obsessive compulsive about things, right? So we've tested at 2 volts and 3, and no, it won't do that. But at 1.5 volts or less, yeah, it's fine. Please.
Do you have a case study yet, or a 10-year look back, UT readings, something like that, to see how it actually performed over time?
I think the early adopter for this technology, Consol Energy in West Virginia, that goes back about 13, 14 years. I think our friends in Pascagoula, I don't think I'm supposed to mention their name. The large oil companies are pretty sensitive about being seen to endorse this technology or any technology. But yeah, some of those things have been coated 2013, I guess. We've got some, the outside of the tanks that you can look at pretty readily, 2016. So yeah, it's been in service for that long. I think the pipes for Sinopec were coated in 2013. And so those are still in great shape. Those are, what was interesting, the folks at Sinopec, that's when we started using a top coat. You don't really need a top coat with this technology, but it's a cement, so cements get dirty over time. So the folks in China, we coated a pretty good sized pipeline for them, and a year later they were stunned. It was the only thing that ever coated along the sea that didn't corrode in a year. But they said, but it's dirty, can you do something about that? So we pressure washed it, we put a top coat on it, and they're happy, and they've continued to be happy with it. So we've begun to tell others that if appearance matters to you, and if it mattered in China, I think it matters elsewhere, we tell people, pick a color you like. We don't manufacture it. We will sell it to you with our label if you want, but
Any other questions?
You can use this for the tank bottoms,
that is correct.
but it's got to be applied in the plant prior to installation. So all the tanks outside of Houston, Pasadena that are corroding from underneath, we can't do anything about that at this stage, right?
You cannot until you have to replace that bottom, which happens all too frequently. Typically, we see people, it seems to range from about 7 years to about 30 that the tank bottoms rust out. It's a big spread. Like my customer in Saudi built, they put oil in the sand so that it would protect the tank bottoms, only it was high sulfur oil, so those rust out in about 7 years now. So that's a very keenly interested customer. But for other places, less. But yeah, when you replace the tank bottom, that's the time to coat it.
Yeah, just to follow up to his question earlier. So have you had a tank that's been in service and undergone a floor scan to just confirm that nothing's happening on the bottom side of the tanks?
We do floor scans, but the coating for the soil-facing side is relatively new. I think we developed this for Honeywell in, 2019, 2018?
2019, then first tank we installed in 2019, late 2019.
Right,
early
so
2020.
Yes, they've tested it, but not enough data to answer it. I think that's why one of the oil majors had Charter Labs do some extensive long-term accelerated testing, and they gave a presentation on that here last year. The analysis is that it's very long-term, but do I have in-service data? No.
Radiation resistance?
This is an educated man here. This technology was developed to shield radioactive waste. That's what it was developed for. Argonne National Labs developed this technology specifically for that purpose. I purchased the rights to do everything else but radioactive shielding. Can it be used for that? Yes. But do I sell it for that? I do not.
Work with control density fill. Control density fill, my site's in love with. Instead of burying lines of dirt, they use, the flowable concretes around the pipes.
I'm not sure I understand the question.
We have buried pipes.
Yep.
And so when we backfill, we use what's called a control density fill, the concrete, the water-like concrete that flows around it to fill all the holes. So I presume it would work, but have you done anything in that application?
I have not. It would work. It bonds well to concrete. You could put it around it. You can use this cement to fill around it if that's what you wanted to do. If you wanted to use this as the fill cement, it would be there forever. The cement has a high amount of phosphate. It is extremely protective.
So any silica-based reaction, any silica-based pozzolanic reaction would bond chemically, covalently with the EonCoat.
Thanks for the great presentation. A couple questions. Is the coating available for use in Canada? And can you do holiday testing?
Good questions. Yes, you can. It's available in Canada. You don't need holiday testing. It's not, it's a porous cement, right? What's relevant is, does the phosphate layer form? What's really interesting with this technology is if you cut a scribe line, like when you test coatings, you cut a scribe line, what will happen in the first few weeks is you'll see red rust in the scribe line. And then the red rust will flake off, and the scribe line will turn will turn black, the unmistakable color of Vivianite. So what happens is it fills in with phosphate and it heals it. Same thing will happen if you have a blemish, like if we have a spot where you miss, it fills in and fixes it. It is an active suppression system.
Got a couple more minutes?
Two-part question. Is there a minimum plate thickness to not sustain burn through? And where you conducted your coating testing, do you know what the pull test results were over the weld path on the bottom side of the plate?
Yes. I think we've tested on as little as 1/8 plate, just for grins, just out of curiosity for ourselves. We welded some plates. Most of my tank customers either use 1/4 inch or 5 millimeter. So that's the standard testing we have. The pull-off strength, interestingly, in Amal's report, I think we showed you yeah, here it is right here. One of the things that she commented on was that the pull-off strength actually went up over time, which surprised us too. We didn't expect that either. What's most important to realize is that pull-off isn't an indicator for this technology the way that it is. So good or bad is not. What's really important about pull-off for polymer coatings is its resistance to osmotic pressure. Right. The resistance to osmotic pressure is what matters, right? That's why we do pull-off tests. And it's a very important thing for barrier coatings. But this isn't a barrier. The barrier is the alloy layer, right? You can't pull that off at 50,000 PSI, right? It's got the tensile strength of steel. You're not pulling that barrier off. It won't come. Now, the cement itself, yeah, that'll come off. It's because the tensile strength of the cement's only 400 or 500 PSI. But it's porous, so you can't build osmotic pressure underneath the cement. Water just comes right through it, right? It goes in and out easily. The barrier is at the metal point, not up top. So we measure it because people ask to measure it, but its relevance, not too much.
Basically, you fail cohesively 100% of time. No adhesion failure. And Lawrence, to your question, you see the scribe line that Tony was trying to explain you.
See the staining around the edge. The cement gets stained, which you see here. You see the cement around the edge, but look at the scribe line, how it heals. Now this is thousands of hours of salt fog here, right? The scribe line starts to bleed, then heals. Active suppression system. This is a change in the fundamental material science of how we protect steel.
Well,
Yeah, just a quick one. Any test results on how this coating performs in an MIC environment?
Another good question. First, realize that what makes MIC is it forms an acid, right? The microbes form an acid. That's why microbial corrosion is severe, is it's acidic. What's really interesting about this technology, pitting corrosion is also acidic. So if we miss a spot, when we're spraying this, when you're spraying a coating, and if we don't get all of the grit out the profile, and so we've missed a spot, it will start to bleed. When it does, the ceramic just extinguishes it. And here's why. The solubility changes as a function of pH. As the pH turns more acidic, it turns loose the phosphate, and it just pours on it, right? And it stops it. Again, active suppression.
Well, thank you. Feels like we could go on, and maybe afterwards, I know I see you off on the side here.
Yeah, that's a good point. Our booth is right there. If you guys want to talk, as you can tell, I like talking about this stuff. I'm a little bit obsessive compulsive, and so I enjoy the interaction. If you want to come, be delighted to talk to you about it as long as you like. Thank you so much for coming. I really appreciate your courtesy.
Thank you so much.